This is Swathi, working as assistant professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal. Welcome to this lecture. In this lecture, we will be discussing about encoders, decoders. These are one of the most important combinational logic circuits, encoders and decoders, and their applications we'll see. So first let us discuss about decoder. So decoder is a combinational circuit that has n input lines and maximum of 2 parent output lines. That means the maximum number of output lines that we can have for a decoder is 2 power n. So one of these outputs will be active high based on the combination of inputs present when the decoder is enabled. So based on the input lines, based on the combination of inputs, so as we have n input lines, so we'll be having 2 parent combinations for inputs. So any one of the output line will be activated or else will be high for any one of the combinations of any one of the 2 parent combinations of input. So the remaining all will be disabled, and this operation will be performed only when the enable input is high. That means when the decoder is enabled. So that means we can say that other than the input lines, we also have one extra input, one control input, that is nothing but enable input. So when the enable input is high, then only the decoder performs its operation. So what kind of operation it is going to perform? So it is going to perform the given binary data or its given decimal data into its equivalent binary representation. So here this decoder that means that here decoder detects a particular code. So the output of decoders are nothing but the minterms of an input variable lines when it is enabled. So as we all know that each combination of input variables is represented as a minterm. Each combination of input variables is represented as a minterm. So here the output decoders or the outputs of the decoder is nothing but the minterms of an input variables or else input lines. And this operation, that means this performs or its regular operation when it's enabled. So decoder is a combinational logic circuit which has n input lines and 2 parent output lines, and it is also having an extra input which is enable input, and the outputs of decoder are nothing but the minterms of n input variables. So this is the given this is the block diagram of decoder. In general, the size of decoder is given by n by 2 power n or else n to 2 power n. So where n represents the number of input lines and 2 power n represents the number of output lines. So here the thing is it converts the given binary data into its equivalent decimal data. So that is the decoder. So decoder converts the given decimal binary data into its equivalent decimal data. So this is the decoder block diagram. So based on the size of the decoder, so as I told you that the size of the decoder is n to 2 power n. So the n may vary from 1, n is equals to 1, 2, 3 and so on. So if n is equals to 1, then the size of decoder, the basic size of decoder or the least possible size of decoder is n, that is 1 to 2, that is 2 power 1. Or else we can also have the least possible decoder is 2 to 4 decoder when n is equals to 2. Now let us discuss 2 to 4 decoder. So 2 to 4 decoder means what? We have 2 input lines and 4 output lines. We have 2 input lines and 4 output lines, and the 2 input lines are represented with A1 and A0, and the 4 output lines are represented with Y3, Y2, Y1 and Y0. And the block diagram for 2 to 4 decoder is given here. So in which we have 2 input lines which are represented with A0, A1 and 4 output lines. Those are represented with Y0, Y1, Y2, Y3, and we have one enable input. So this enable input may be in either active low or active high. So as we don't have a bubble here, this is active high. That means when the enable input is 1, then the decoder is enabled and it performs its operation. Okay, so and as I told you that decoder, any one of the output line will be active high. That means any one of the output line will be equal to 1 for each of the combination of input, and all the other lines becomes 0. And this happens only when enable input is equals to 1. Now based on this, we can have the truth table for this one. So that means as we have two inputs, what are the possible combinations we can have? 2 par 2, 4. What are the four combinations? 0, 0, 0, 1, 1, 0, 1, 1. So this is A1, A0. So which line is enabled? As we have three output lines, Y3, Y2, Y1 and Y0. So as I told you that for every combination of input, only one output line is enabled. So which line will be enabled? So here, as it is 0, 0, the decimal equivalent of this one is 0. So the output line whose subscript is equals to decimal 0 will be enabled. That means will be equal to 1 and the remaining all becomes 0. So Y0 is 1 and the remaining all are zeros. Now coming to 0, 1, what is the decimal equivalent of this one? This is 1. So and hence Y1 is 1 and the remaining all are zeros. So like that we can have the truth table here. So this happens only when enable input is high. So here this is the enable input. So when enable input is 0, irrespective of the input, or as a decoder is said to be disabled, so all the outputs are equal to 0. So this is the thing we need to remember. When the enable input is 0, whatever it may be the input, that means whatever it may be the input applied to the A1 and A0, all the outputs are disabled. That means all the outputs are equal to 0. And the decoder performs its operation whenever when the enable input is high. Now let us consider that enable input is high. Now the inputs applied are 0, 0. So what is the decimal equivalent of this one? This is equals to 0 and hence Y0 is high and the remaining all are zeros. Now enable is 1 and this is 0, 1. So the decimal equivalent of this 0, 1 is 1. So Y1 is 1 and hence the remaining three inputs outputs are zeros. Now A1 is 1 and A0 is 0. So what is this? The decimal equivalent is 2. So that means Y2 is high, the remaining three are zeros. 1, 1 as a decimal equivalent is 3. So Y3 is 1 and the remaining all are zeros. So this is the truth table of 224 decoder, and one thing we have to remember, the decoder is enabled and performs its operation only when the enable input is high. When the enable input is low, irrespective of the input, all the outputs will become 0. So this is the decoder truth table. Now coming to the Boolean function. So based on this, we can write down. So when the Y0 is 1 only for one combination. What is that combination? A1 is equals to 0, A0 is equals to 0 and enable is 1. So I can say that Y0 is equals to, as enable input is high, so we have to take it in true form, and A1 and A0 are 0. So A0 complement, A1 complement. And similarly, Y1 is 1 only for one combination. That combination is 1, 0, 1. So Y1 is equals to A0, A1 complement A0, because A1 is 0 and A0 is 1. And Y3 is 1 for only one combination, which is 1, 1, 0. So sorry, Y2 is equals to, enable is high and A1 is also high, whereas A0 is 0. And similarly, Y3 can be written as A1, A0. So these are the logical expression for all the outputs. For always you remember, Boolean expression can be written for all the possible outputs in terms of inputs. So as we have taken three inputs here, E, A1, A0. So I am writing the expression for Y0 as we have four outputs. So we need to write the logic functions or else Boolean functions for all the four outputs, and those are this one. So that is Y3 is equals to E, A1, A0, and Y2 is equals to E, A1, A0 complement, and Y1 is equals to E, A1 complement, A0 plus Y, and Y0 is equals to E, A1 complement, A0 complement. So this is the logic circuit. Based on this Boolean expressions, we can draw the logic circuit. So first I am taking A0, okay, and its complement. Next, A1 and its complement. So this line is A0. Okay, this line is A0 and this line is A1 complement. Okay, and this line is A0 complement and this line is A1 complement. So here, sorry. So this is A1, right? So this is A1 complement. Now, coming to this one, this is A0. From A0, I am taking an inverter. So this line is A0 complement. And what about this one? This line is taken from A1. So directly it is given A1. Whereas this is taken from A0. This is A. So now Y0. What is Y0? Y0 is A1 complement. And next A0 complement. This line is A0 complement. And this line is enable. So enable input is high for all the outputs. So that is why enable is given to all the logic gates here. And what kind of logic gates we need to use? As these are all the product terms, I have to use the AND gates. So this is enable. So the output of this one is enable, A0 complement, A1 complement. Now coming to this one, this is coming here. This is A0 and A1 complement, and this one is enable. So that is enable, A1 complement and A0. Next coming to this one, A1 is coming and here A0 complement is coming. This is A0 complement and enable. So Y2 is equals to enable, A1, A0 complement. And now for this one, so A0 is coming and A1 is coming and enable. So A1, A0 and this one is equals to enable, A1, A0. So this is the implementation of a 2 to 4 decoder. So 2 to 4 decoder is having 2 input lines, 1 enable input and 4 output lines. At any that means any one of the output line will be high for the given input combinations, and this happens only when the enable input is logic high. Now coming to the 3 to 8 decoder. So the next possible decoder is when n is equals to 3. So what is the size of decoder? So the decoder size is 3 to 2 power 3, that is 3 to 8 decoder. 3 to 8 decoder. So this decoder is also called as binary to octal decoder. So as I told you that we have the decoder is converting given binary data into decimal data. So how many number of outputs we have? We have only 8 outputs. So that is why we can say that it is converting a given 3-bit binary data into its equivalent octal data, where the octal symbols are 0 to 7. So that means a 3 to 8 line decoder will have 3 input lines, 8 output lines, and the 3 input lines are represented with A0, A1, A2, and the 8 output lines are represented with Y0, Y1, Y2, Y3, and so on, Y7. And anyhow, we'll have enable input. We'll have enable input E. So this is the 3 to 8 decoder. So now, as similar to the 2 to 4 decoder, this 3 to 8 decoder is enabled, or else it performs its operation only when the enable input is high. Okay, so when the enable input is 1, depending on the input combination, any one of these 8 output lines will be high and the remaining 7 output lines becomes 0. So based on that, this is a truth table. So if enable input is 0, irrespective of all the inputs, that is don't care I have used, whatever it may be the input combination, if enable input is 0, so whatever it may be the input applied, all the output lines are 0. And when the enable input is 1, depending on the input. So now the input may be 0, 0, 0. So what is the decimal equivalent of this one? This one will be 0. So as it is 0, so Y0 will be high and the remaining all will be zeros. Similarly, 0, 0, 1, decimal equivalent is 1. So Y1 is 1, remaining all are zeros. And 0, 1, 0, enable input is high. So and hence this is 1, Y2 is 1 and the remaining all are zeros. Like that, we can form the truth table for the given input combination. Any one of the output line is enabled, that means active high, and the remaining all are zeros. So which line is to be equal to 1? How can we decide? So we need to identify the decimal equivalent of the combination given to the input lines. So that particular output line which is having its subscript equal to the decimal equivalent is high and the remaining all are zeros. So this is 3 to 8 line decoder. Coming to the logic functions, so we can have enable input. It is an optional one. We can have enable input or not, but you need to remember we can have enable input. So I'm not mentioning enable input here. So why not? Why not is equals to, it is high when A0, A2, A1, A0 all zeros. That means I can say that Y0 is equals to A2 complement, A1 complement, A0 complement. This is Y0. And Y1. So go through the truth table. So Y1 is equals to what? Y1 is becoming 1 when A2 is 0, A1 is 0, A0 is 1. So A2 complement, A1 complement, A0. Similarly, Y2, so 0, 1, 0. So that is A2 complement, A1, A0 complement. And Y3, so I can write this one as A2 complement, A1, A0. And Y4, what is the binary equivalent? 1, 0, 0. 1, 0, 0 means A2, A1 complement, A0 complement, and so on. So Y5. Y5 means this is 1, 0, 1. 1, 0, 1 means A2 and A1 complement, A0. Next, 1, 1, 0. 1, 1, 0 means A2, A1, A0 complement. A2, A1, A0 complement. 111 means A2, A1, A0. So these are the Boolean expressions for the 3 to 8 decoder, and this is a logic function based on this logical expression for all the outputs. So here Y0 is equals to, so this is A0, A2 complement, A1 complement, A0 complement. So this is the output. Now coming to Y1, A1, A2 complement, A1 complement, A0. And similarly, we can draw the logic circuit based on this expression. I hope it is clear. So nothing is there. Once you have the Boolean function, you can draw the logical diagram or else logic circuit based on this Boolean expression. As we have 8 outputs, so we have to use 8 AND gates, and all of these are product terms. So in order to implement these 8 output functions, I require 8 AND gates. So if you have enable input, you have to provide one more input for all the logic gates. This is enable like that. Okay, so that is an optional one. So this is the 3 to 8 decoder. Now coming to the we can 4 to 16. We can also have 4 to 16 and 4 to 16 decoder, 5 to 32 decoder and all. So in order to implement 4 to 16 decoder, how many logic gates are required here? 16 AND gates. And what are the number of inputs to this? That is minimum 4 or maximum 5. Including 4 inputs and 1 enable input, we can have 5 inputs. And and also we require 4 inverters, and also we require 4 inverters. So this circuit will become complex. Even if you go for 5 to 32, I require 32 AND gates with minimum of 5 inputs or maximum of 6 inputs, and 5 inverters we require. So that means as the size of the decoder is increasing, the complexity of the circuit becomes more. So in order to avoid this, we can implement the higher order decoders by using lower order decoders. So as already we know, we have implemented 2 to 4 decoder and 3 to 8 decoder. So making use of this 3 to 8 decoder and 2 to 4 decoder, we can implement 4 to 16 decoder and 5 to 32 decoder and so on easily. Without that means with less complexity, we can implement all the other higher order decoders. Now let us see how to implement a 3 to 8 decoder using 2 to 4 decoders. How many decoders are required first of all? So first of all, we know that a 2 to 4 decoder has 2 inputs and 4 outputs, right? So the 2 inputs are represented with A1, A0, and 4 outputs are Y3, Y2, Y1 and Y0. Now, I want to implement a 3 to 8 decoder using 2 to 4 decoder. So where in 3 to 8 decoder, I have 3 inputs and 8 outputs, and the 3 inputs are represented with A2, A1, A0, and 8 outputs are represented with Y7 to Y0. So now the implementation. So how can we find how many number of decoders or lower order decoders are required for implementing higher order decoder? So for that we have a formula. So in order to find out the required number of lower order decoders is equals to M2 by M1. What is M2? M2 and M1. So M1 is a number of outputs of lower order decoder and M2 is a number of outputs of higher order decoder. So now what I want to implement, I want to implement 3 to 8 decoders. 3 to 8 decoder, right? 3 to 8 decoder, what is the number of outputs? So higher order, the number of outputs in higher order decoder is represented with M2. So where M2 is equals to 8. So whereas with which I want to implement with 2 to 4 decoder. In 2 to 4 decoder, how many outputs we have? 4. So which is represented with M1. So M1 is equals to 4. Now based on the formula M2 by M1, so 8 by 4, that is equals to 2. So that means I require 2 to 4 decoders to implement a 3 to 8 decoder. For example, I want to implement a 4 to 16 decoder. 4 to 16 decoder using 2 to 4 decoder. So then using 2 to 4 decoder. So this is higher order. So higher order decoder outputs are represented with M2, where the number of outputs is equals to 16. Whereas in this one, the number of output is equals to 4. So 16 by 4. So how much? That is 4. That means I require 4 2 to 4. I require 4 2 to 4 decoders to implement a 4 by 16 decoder. So this is the decoder size. How can we decide the number of decoders that can be used in order to implement higher order decoders using lower order decoder? The formula that you have to remember is M2 by M1, where M2 is the number of outputs of higher order decoder, whereas M1 is the number of decoders, number of outputs of lower order decoder. So this is enough. Now I want to implement a 3 to 8 decoder using 2 to 4 decoder. So now according to the formula, so we require 2 to 4 decoders for implementing a 3 to 8 decoder. So this is the block diagram of 3 to 8 decoder which can be implemented using 2 to 4 decoder. So actually we have in 3 to 8 decoder, we have 3 inputs, A2, A1, A0. So what are the combinations? 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So we have an enable input. Okay. So if you observe A1 and A0, so A1 and A0 are varying from 0, 0 to 1, 1, whereas A2 is 0 for the first 4 combinations and A2 is equals to 1 for the next 2 combination. So what we want to remember is always whenever you are implementing higher order decoders using lower order decoders, so the MSB is to be considered as enable input, and this should be applied as it is for the upper decoder, and a complemented enable input or complemented A2 will be applied as enable input to the lower decoder, so that we can decode all the possible combinations of higher order decoder. So we are taking 2 to 4 decoders here, 2 to 4 decoders. Each one is having 2 inputs here. This is A1, A0. This is A1, A0. And we have 4 outputs here. Each is represented with 0, 1, 2, 3, 0, 1, 2, 3. Okay. So Y0, Y1. I have given the names of outputs as Y0, Y1, Y2, Y3. So actually how many outputs we have? We have 8 outputs, Y7 down to Y0. So I am giving the names of lower order output, names to the output lines of lower order decoder with Y0, Y1, Y2, Y3, and upper decoder with Y4, Y5, Y6, Y7. Now, I told you that A2 is taken as enable input and A2 is directly applied as enable input for the upper decoder, and it is complemented and applied as enable input to the lower decoder. Whereas the remaining 2 inputs A0 and A1 are applied as inputs to the decoders, two decoders, 2224 decoders as a common. So now let us try to decode. For example, my input combination is 110. So actually in 328 decoder, which output line should be enabled? I6 should be enabled, and the remaining all are, that is Y0 to Y5, and Y7 should be equals to 0. Now we'll verify whether this is happening or not. So here now as A2, this is A2, this is A1, and this is A0. So as A2 is equals to 1, so which is given as enable input to this one, whereas it is complemented and it is given. So what happens? The lower decoder will be disabled, and hence the outputs are all equal to the 0 in case of lower decoder. Now coming to this one, as it is enable input is high, so this is enabled. Now it depends upon the input line. So here, and whatever it may be, the inputs applied are A1 is equals to 1 and A0 is 0. This is 1 and this is 0. So as it is 0, as the enable input is 0 here, irrespective of this combination, go to the truth table, you can understand. If enable input is 0, whatever it may be the input applied, so all the outputs are equal to 0. But here the enable input is high. Now it will check the input applied. So what is the input applied here? 10. What is the decimal equivalent of 10? That is Y2. So here this line will be enabled. That means Y6 is equals to 1 and the remaining all are zeros. So this is what the operation. Okay, so similarly you can check for any other combination. For example, let us consider 0, 1, 1. Okay, let us consider for 0, 1, 1. Now what happens? Let us see. Okay, so here now 0, 1, 1, that means A0 is 0. That means A0 is 0, right? A0 is 0, A2 is 0. So in that case, this is 0. And what are the inputs that are applied? A1 is 1 and A0 is also 1. So as enable input is 0, so this upper decoder will be disabled, and hence the outputs of this upper decoder are all equal to 0. Now as it is 0, it is complemented and it is 1. So now the enable input is 1. So now the lower decoder is enabled, and now it will check the inputs applied to the A1 and A0. So the inputs applied to A1 and A1 are 1 and 1. So and hence this 3 is enabled. What is the decimal equivalent of 1, 1? 3. So this line will be high and the remaining all are zeros. What is the decimal equivalent? 3. So Y3 is high, remaining all are zeros. Like that, the decoder will decode the given input combination. That means it converts the given binary data into its equivalent decimal data. So this is the implementation of higher order 328 decoder using 224 decoder. Now let us try to implement a 4 to 16 decoder. 4 to 16 decoder using 3 to 8 decoder. I want to implement a 4 to 16 decoder using 3 to 8 decoder. So in 3 to 8 decoder, what is the number of output? That is M1 is equals to 8. Whereas in 4 to 16, what is the number of output? That is higher order decoder, M2 is 16. So here now I can find out the value, that is M2 by M1 is equals to 16 by 8, which is equals to 2. That means in order to implement a 4 to 16 decoder, I require 2 3 to 8 decoders. Whereas in 3 to 8 decoder, we have 3 inputs which are represented with A2, A1, A0, and 8 outputs. Those are Y7 to Y0, Y7 to Y0. And in 4 to 16 decoder, we have 4 inputs A3, A2, A1, A0, and 16 inputs Y0, Y50. And as I told you that I require 2 3 to 8 decoders, and in which as we have 4 inputs in a resulting decoder, so the MSB, which is A3, is taken as enable input, so which is given as it is in true form to the upper decoder and in complemented form to the lower decoder. Okay, so the remaining 3 inputs are applied as inputs to the 2 3 to 8 decoder as a common. So this is the implementation of 4 to 16 decoder using 2 3 to 8 decoder. So we have taken 2 3 to 8 decoder which are having 3 inputs. So these 3 inputs are A0, A1, A2. So these are this is also having 3 inputs, A0, A1, A2, and the enable input is MSB is given as enable input. So MSB A3 is given as enable input, and it's complemented and again given as enable input to the lower decoder, right? So now as we have 8 outputs here, 0, 1, 2, 3, 4, 5, 6, 7. So the output lines of lower decoder are designated as Y0 to Y7, whereas the output lines of upper decoder are represented as Y8 to Y15. Total, how many output lines we have? 16. Now, for example, let us consider 1, 1, 1110, A3, A2, A1, A. Now, what is the equivalent here? 12 plus 2, 14. 14th line Y14 should be equals to 1 and the remaining all should be 0. Now, let us decode this one. So, A3 is 1. So, this is enabled, whereas this is 0. So, this is disabled. Okay. This is disabled. This is enabled. Right. So, now what is the combination here? The remaining combination is 1, 1, 0. Right. This is also 1, 1, 0. Right. So, now as this is disabled, so whatever it may be the input applied, so all the outputs of lower decoder will be 0. Now, coming to the upper decoder, as enable input is 1, this is enabled. And now what is the input applied here? 1, 1, 0. That means 6th input will be enabled. What is the 6th input? 6th output. This is the 6th output, which is equals to Y14 will be high, and the remaining all are zeros. So, Y14 is enabled and the remaining all are disabled. So, this is how you can implement any other decoder, any higher order decoders using lower order decoders. Now, what are the advantages of decoders? Where we can use? What are the applications of decoders? We can use these decoders in the designing of code converters, used in memory system of computers to access a particular memory location based on the address produced by the computing network. That means address decoding. Mostly we use in microprocessors and all. So, in order to decode the address of the memory location, we always use decoders. And one more application is here to carry out the operations in arithmetic logic unit of CPU. Decoders are used to decode the program instructions to activate the control lines. So, not only decoding the address lines or else address of the memory location, it is also used to decode the programming instruction such that control lines are activated. So, these are the major applications of decoders. Now, coming to the next topic, that is encoder. So, it is also a combinational circuit which performs the reverse operation of decoder. So, what is the operation performed by the decoder? It converts a given binary data into decimal data, whereas the encoder performs reverse operation, that is, it converts the given decimal data into binary data. Okay, so as I told you that it is a reverse operation of decoder. So, what are the number of input lines we have in decoder? N, and 2 pair n output lines. So, the input and output lines are also different. So, 2 pair n input lines and n output lines. So, this is the generalized size of encoder, which is having 2 pair n input lines and n output lines. Okay, so now the encoder, an encoder is a combinational logic circuit which is having 2 pair n input lines and n output lines, which is used to convert the given decimal data into binary data, and at any time only one input line is activated. So here, whereas in the previous case, at any time only one of the output line is enabled, but here it is opposite. At any instant of time, only one input line is activated, and the produced n-bit output code is equivalent to the binary information. So, whatever the line that is activated, whatever the input line that is activated, that is going to be converted into binary. So, that means the output n-bit output code is equivalent to the binary information of the input line which is activated. So, this is the block diagram of the encoder, which is having 2 pair n input lines and n output lines. Okay, so here the least possible size of encoder is 4 to 2 encoder. So, where when n is equals to 2 we are considering. So, if n is equals to 2, 2 pair n inputs to n outputs, so that is 4 inputs to 2 outputs. So the given 4 inputs are converted into 2 output lines. So here, as I told you that at any instant of time, any one of the input line is enabled. So that means as we have 4 inputs here, so if it is a binary combination, I should have 16 input combination. But as I told you that in encoder, at any instant of time, only one input is enabled. So I have only 4 combinations of inputs. I have only 4 combinations of input. So now let us see the 4 to 2 line encoder, which is having 4 inputs and 2 outputs. 4 inputs are represented with Y0, Y1, Y2, Y3, and 2 outputs are represented with A0, A1. So here, now let us see the block diagram. So this is the block diagram of 4 to 2 encoder. So 4 input lines, Y0, Y1, Y2, Y3, and A0, A1 are the output lines. Now let us see the truth table here. So as I told you that at any instant of time, any one of the input line is enabled. So let us consider Y3 is enabled. So actually these are considered to be active low. So here, if you consider these as active high inputs, so I can see that Y3, Y2, Y1, Y0 and A1, A0. So these are the inputs and these are the outputs. So these are for active low outputs. Okay. So here now actually when Y0 is enabled, then the output will be 0, 0. When Y1 is enabled, so that this is 1. Then in that case 0, 1. When Y2 is enabled and all are zeros, so what is Y2? Binary equivalent of 2 is 1, 0. Next, when Y3 is enabled, 1, 1. So this is the truth table of this 4 to 2 encoder. So at any instant of time, only one input is considered to be 1. So here we will also have enable input for this one. This is an optional one. If the enable input is again 0, so what happens? That or else if all the inputs are all 0, then also what should be the output? Then also the output should be 0, 0. So here this is the major ambiguity of normal encoder. So we are getting the output 0, 0 for 2 conditions. One, that is when Y0 is equals to 1, and also when the encoder is disabled, or else when all the inputs are equals to 0, the output is also 0, 0. So this is the ambiguity and this is a drawback of encoder. That means based on this output, I could not decide whether all the inputs are 0 or whether Y0 is 1. Okay. So this is the ambiguity and this is a major drawback of encoder. Okay. So now based on the truth table, now how can I decide this one? How can I draw the equivalent, how can I derive the Boolean expression for 2 outputs A1 and A0? So A1 is 1 in both in 2 condition, when Y1 is equals to 1 or Y0 is equals to 1. Y1 is equals to 1 or Y0 is equals to 1. So that is why I can write A1 as Y1 or Y1 or Y3. So here if you see, A1 is becoming 1 for 2 combinations. So sorry, actually not this. So A1 is 1 for 2 combinations. What are those? Y2 and Y3. That means when Y2 is 1, A1 is 1. And also when Y3 is 1, A1 is also 1. So I can write A1 as Y2 or Y3. Y2 or Y3, or else Y2 plus Y3. Similarly, A0 is becoming 1. In which condition? A0 is becoming 1 when Y0 is equals to 1. Either if Y0 is 1 or Y1 is 1. So A0 can be written as Y0 plus Y1. So these are the equations. So this is Y0 plus Y1, Y3 plus Y2. Okay. So this is the condition. So and hence we can say that we can write down the equation like Y0 Y1 plus Y3 Y2, Y3 plus Y2, or else you can also consider this condition 0, 0. Okay, so in that condition also we can see this one. So like that we can have the expression for this Y0 and Y1, that is Y2 So based on this active low output, so I can say that A0 is becoming 1 when Y2 and Y3 are, when Y2 is 1 and just a second. A0 is 1 when Y2 is 1 and also Y0 is 1. Okay, so from based on this, A0 is equals to Y2 plus Y3. Similarly, A1. So when it is becoming 1, so I am removing this. So A1 is becoming for Y1 is 1 and also Y0 is 1. So Y1 plus Y. Okay, Y1 plus Y0. So like that, I can draw the logic circuit for this one by taking the inputs here. So I'm writing here. I'm drawing the logic circuit. So I'm taking an OR gate, 2 input OR gate such that A1 is implemented. So what is the A1 equation? Y2 plus Y3. Y2, Y3. And for this one, this equation is A0 is becoming 1, Y2 plus Y0. Okay, so Y2 is this one. So Y2 plus Y0. Okay, Y2 plus Y0 and this one is Y2 plus Y3. So this is the circuit when we consider the outputs as active low. Whereas this is the equation when we consider the outputs as active high. Okay, so this is the circuit for the active low outputs. So that is about 422 encoder. Now let us see the 823 encoder. So in 823 encoder, we have 8 input lines, 3 output lines. So we can also call it as octal to binary encoder. So we have 8 inputs. So these 8 inputs represents the symbols of octal number system. So those are Y0, Y2, and Y1, Y2, and so on, Y7. And 3 inputs we have, 3 outputs we have, A0, A1, A2. So this is a block diagram of 823 encoder. And coming to the truth table, so here when Y0 is 1, remaining all are zeros. So what happens? The output is equals to 0, 0, 0. Now when Y1 is 1 and the remaining all the inputs are 0, then the output is equals to 0, 0, 1 and so on. When Y7 is 1, so the output is equals to 1, 1. So now let us write down the equation for this. So in A2 is becoming 1 for the 3 combination, that is Y4, Y5, Y6, Y7. So Y4 plus, Y5 plus, Y6 plus, Y7. What does it mean? A2 becomes 1 for Y4 when Y4 is 1 or Y5 is 1 or Y6 is 1 or Y7 is 1. So that is why I can write this as OR. And similarly, Y2. A2 is 1 for the combination. This is for Y2 and next Y3 and next Y6. Okay, and then Y7. So Y2 plus Y3 plus Y6 plus Y7. Now let us see the other combination, that is A1. We will see the output equation for A0. So 0. So this is Y1 when Y1 is 1 and then Y3 is 1. Okay, Y3 is 1. Then Y5 is 1. Y7 is 1. So that means Y3, Y1, Y5 plus Y7. These are the equations. So this is the implementation of that 823 encoder. So I am taking Y1, Y2, Y3, Y4, Y6, Y7. So A2 is equals to Y4 plus Y5 plus Y6 plus Y7. And similarly coming to A1. So A1 is equals to, let us see the equation, Y2, Y3, Y6, Y7. So Y2, this is Y2. Okay. Sorry, this is Y3. And this one is Y2. And this one is Y7. And coming to this is Y6. Okay. So Y2 plus, Y3 plus, Y6 plus, Y7. Coming to this equation, Y1, Y3, Y5, Y7. Y1, so this is Y1 and this one is Y3. This is coming here. This is Y3. Next Y5 and this one is Y7. Okay, so A0 is Y1 plus Y3 plus Y5 plus Y7. So this is the logic circuit of 3 to 8 encoder. So now, like that, you can implement any other sizes of encoders, that is 16 to 4 or 32 to 5 encoder. Like that, you can implement any other encoder sizes. But the major drawbacks that we can observe in an encoder. So what is the drawback that we can observe? At any instant of time, only one input line is enabled and the remaining all the input lines are considered to be 0, because it could code the corresponding inputs when only the least significant input is 1 or when all the inputs are also equals to 0. That means the output becomes all 0 condition when the least significant bit is 1, that is when y0 is equals to 1, or when all the inputs are equal to 0 also, you will get the same output. So this is this is the disadvantage of encoder. And one more drawback we can observe. So at any instant of time, if more than one inputs are enabled, for example, we have a 823 encoder. So we have 110 combination. That means, we have two input lines are activated here. So for example, if both Y3 and Y6 are high in a 823 encoder, if Y4 or Y6 are high, Y4 and Y6 are high, then it gives an ambiguity. So which input line should be encoded into binary? Which input line should be encoded into binary? So the output may be either 100 or 110. Okay, so because at a time both the input lines are activated. So in such case, the encoder will not be able to encode the given input lines into binary. So these ambiguities should be avoided. So these are the major drawbacks that we can observe in an encoder. What are the two major drawbacks here? So we have the output combination, that is all 0 output condition happens when all the inputs are 0 and also when the least significant input line is high. So this leads to an ambiguity. So that means at the output side, we'll have a confusion whether the input line is high or all the input lines are 0. So this is an ambiguity. And the other ambiguity is when more than one input lines are activated, the encoder will not produce a correct encoded data for neither of the input lines encoded. That means it will be in confusion which one is to be encoded. So these are the two drawbacks that we can observe in a normal encoder. So to overcome these difficulties, we are going for another type of encoder, which is priority encoder. What we are doing in priority encoder? We should assign priorities to each input line of the encoder, and if more than one input lines are enabled, based on the priorities given, the input line which is having highest priority will be encoded into binary first. So such type of encoder is called as priority encoder. So what we are doing in priority encoder, so each input line is given a priority such that, for example, we have 422 encoder, Y3 will have highest priority when compared to Y0. So Y0 is having lowest priority and Y3 is having highest priority. So if Y3 is enabled and Y0 is also enabled, so as Y3 is having highest priority, this is going to be converted into binary. So whereas in normal encoder, it leads to an ambiguity which one is to be converted into binary. But as we are assigning the priorities based on the highest priority, that line will be converted into binary. So this is a priority encoder. So let us see the 422 line priority encoder. So 422 line priority encoder is having 4 inputs, such as similar to the 422 normal encoder, and 2 outputs again, A1, A0. Here the input Y3 has the highest priority, and whereas Y0 has the lowest priority. As I told you that each input line is assigned with priority. So the input line Y3 is having highest priority and Y0 is having lowest priority. In this case, even if more than one input is enabled or else high at a time, the output will be the binary code corresponding to the input which is having highest priority. So now let us see the truth table of 4 to 2 line priority encoder. So in this, we will consider one more output V in order to know whether the code is available and the output is valid or not. So to decide whether the output code is valid or not, we are using one more output in the table, which is V here. So if at least one input of the encoder is 1, then the code available. So this is how, we have two ambiguities in encoder, right? First one is we have output is 0. All the output lines are 0 in both the conditions. What are the conditions? When all the input lines are 0 and when the least significant bit is enabled or high. So in order to avoid this, we are having another one more output, which is V. So this, if at least one of the input line is high, then the V output is considered to be 0. The V output is considered to be 1. In this case, the output V is equals to 1. So that means if any one of the input of the encoder is 1, then the code available at the output is a valid code and hence V output is considered to be 1. And when the V output is considered to be 0, so when if all the inputs of the encoder are 0, that means none of the input is high, that is logic 1. In that case, the code is considered to be not valid. So we should not have such type of condition. So for that, this is to be considered as not valid condition. In such case, the output voltage, output variable V will be considered as 0. So this extra output we are considering in order to avoid the ambiguity of all 0 output condition, which happens in 2 cases. Okay. So now here this is a truth table. When all the inputs are zeros, irrespective of the input the output will be don't care. We don't consider the output variables, and the output V should be considered as 0 because this is not a valid input code. Okay, so if any one of the input line is high, then only it is considered as valid input code, right? So as it is invalid, so we are considering the V output as 0. Now coming to the Y2, Y3, Y2, Y1, Y0. So when all the inputs are zeros and only Y0 is 1, as this is having the highest priority because all the other higher priority inputs are zeros, so only this is going to be converted in binary. So that is 0, 0, and as it is a valid code, it becomes 1. Next up, if Y1 is 1, so and Y0 is don't care. So as Y1 is 1, why I am writing Y0 as don't care? Because as Y1 is having highest priority when compared to Y0. So whatever it may be the value of Y0, if Y1 is 1 and Y3 and Y2 are zeros, so when compared to this is having highest priority and as it is enabled, so whatever it may be the value of Y0, so as Y1 is 1, so Y1 is going to be converted into binary 0, 1 and it is a valid code and hence we are writing it as 1. Now, in order to encode this 2 into binary, so what should we consider? Y3 should definitely 0 because Y3 is having highest priority. If it is 1, then definitely this will be converted into binary. As I want to convert this Y2 into binary, definitely Y3 should be 0 and Y1 is 1 and whatever it may be the value of Y1 and Y0. So that means this is having highest priority. Whatever it may be the values, as it is having highest priority, this one will be converted into binary. So value of this output is 1, 0 and V1 is considered to be 1 because it is a valid code. Now, as Y3 is having highest priority, as it is 1, whatever it may be the values of this Y2, Y1 and Y0, so it will be converted into binary 1, 1 and it is a valid code. So now let us draw the logic circuit for 4 to 2 line priority encoder. So we are taking the logic K map for simplifying the expression for A0, A1 and also V. So here A0, A1. So as we have 4 input lines, so y3, y2, y1, y0. So I am mapping this. So let us see the A1. So A1 is 1 for 0, 1, don't care, don't care. 0, 1, don't care, don't care. So let us see 0, 1, don't care, don't care. Okay, and let us see, this is don't care and don't care for 0, 0, 0, right? So that is why it is for 0, 0, 0, 0, it is don't care, and for all this combination it is marked with 1. So what does it indicate? 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1. So that means 4, 5, this is 4, 5, 6, 7. Okay, 4, 5, 6, 7, and also 4, 5, 6, 7. This is one combination. And the next one is 1 triple don't care. 1 triple don't care. 1 triple don't care means this starts from 8. 0, 0, 0 to 1, 1, 1. That means 1, 0, 0 to 1, 1, 1. That means 8 to 15. So 8 to 15 and 4 to 7. So 4, 5, 7, 6, 8, 9, 11, 10, 12, 13, 14, 15. For all this is marked as 1. Whereas 0, 0, 0, 0, it is don't care. So for the remaining combinations, it is 0. So now I can form 2 octets here. So the first octet, I can write it as, so for this one, y3 value is common where y2 is varying, eliminate y2, and y1 and y0 are varying for all these 8 cells. So eliminate y1 and y2. So this is y3. And for this one, so y3 is varying, eliminate, where y2 is common and it is equals to 1. And whereas y1 and y0 are varying, eliminate. So a1 is equals to y3 plus y2. And similarly, now a0 is becoming 1 for 0, 1, 0, 0, 1 don't care. This is one combination. And the second combination is 1 don't care, don't care, don't care. And similarly, it is don't care for 0, 0, 0, 0. So now 0, 0, 0, 0, 1 don't care. 0, 0, 1 don't care means don't care may be either 0 or 1. So 0, 0, 1 is constant, whereas this may be 0 or this may be 1. So what is the equivalent of this one? This is 2 and this is 3. So 2 and 3 are marked with 1. And the next combination is 1 triple don't care. 1 triple don't care means 1, 0, 0, 2, 1, 1, 1, which is 8 to 15. 8 to 15. So now I marked 8 to 15 as 1 here. So 8 to 15, these are ones, actually not don't cares. These are ones, whereas this is don't care. So now I can form an octet with this. Always we will try to form higher groups. So we form an octet, and in order to cover these two, I can form a quad with this. I can form a quad with these two. So that now what is a octet? What is the equivalent prime implicant for this one? As y3 is common, y3, and it is equals to 1, whereas y2 is varying and y1, y0 are also varying, eliminate. Now coming to this quad, so y1, y3, y2, sorry, not this one. So it is formed with first row and last column. For the first row and last column, y3 is varying, eliminate, y2 is common, so y2 complement, and first, second, third column and fourth column. So y1 is common, consider y1, whereas y0 is varying, eliminate y0. So y1, y2 complement. So a0 is equals to y3 plus y1, y2 complement. And similarly, you can write down the equation for V. So what is the equation for V? So equation for V is, okay, V is equals to, so we can draw the equation for V. So how can we draw the equation for V? 0, 0, 0, 1, 0, 0, 1 don't care, 0, 1 don't care, don't care, 1 don't care, don't care, don't care, right? So now I could draw the K-map for this one. So what is that? So I can draw the K-map here for V output. So y3, y2, y1, y0. So I have a 4 variable K-map here. So 0, 0, 0, 1, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, right? So now what are the combinations we have? 0, 0, just we'll see the combination. 0, 0, 0, 1, Okay. 0 0, just will write 0 0 0 1, 0 0 1 don't care, 0 1 don't care, 1 don't care. 0 0 1, 0 0 1 means 1. Okay. And 0 0 1 don't care means it is 2 and 3. It is 2 and 3. And next this one is 4 5 6 7. So 4 5 6 7. Next 8 8 9 11 10 12 13 14 15. So now what I can form, I can form 4 octets here. This is one octet, this is one more octet, and let us see. Let us use another color. So this is one more octet, and this one is one more octet, right? So like that 4 octets I can form. So the first octet, so as y3 y2 are varying, eliminate, whereas y1 is common, so this is y1. And for this one, so y3 y2 are varying, eliminate, y1 is varying, eliminate, y0 is common, so y0. Now coming to this squad, so y1 y0 are varying, whereas this is common, so y3, whereas for this one y2, so that is why v is equals to y0 plus y1 plus y2 plus y3. Okay, so this is the expression, whereas a0 is equals to a1 is equals to y3 plus y2, y3 plus a1 is equals to y3 plus y2, whereas this one is equals to, so y3, this is y3, okay, plus y2 complement, this is y2 complement into y1. So this is y2 complement into y1. So y1 into y2 complement. This is it. So this is the logic circuit for priority encoder, and the priority encoder is mainly used to avoid the drawbacks of this encoder, normal encoder. Now coming to the advantages of priority encoder. So these systems are very easy to use in all digital systems, and encoders are used to convert the decimal number into its equivalent binary number, and the objective is to perform the binary operations such as addition, subtraction and multiplication, etc. So these are the major applications of encoder. So that's all for this lecture. I hope it is clear to you all. We have discussed encoders, various types of encoders, and the drawbacks of encoder, and what are the advantages of priority encoder, and the difference between priority encoder and normal encoder. And we have also seen the various types of decoder and the applications of decoder in this lecture. I think it is clear to you all. Thank you everyone.
Like, share and subscribe. Hit the bell icon for more updates.